Bien, pues muy buenos días. En nombre del Instituto Mexicano de Tecnología del Agua y de la Cátedra UNESCO IMTA El Agua en la Sociedad del Conocimiento, les damos la más cordial bienvenida a este nuevo espacio de conocimiento en línea, con el cual pues conformamos esta comunidad de análisis, de conocimiento de los temas fundamentales para el conocimiento y la gestión del agua. Yo los saludo con muchísimo gusto. Mi nombre es Marco Sánchez y estamos ya todos listos para comenzar con este interesante tema. Si entre tus temas de interés está las inundaciones urbanas, estás en el mejor espacio, en el mejor lugar con esta presentación que tendremos esta mañana del doctor Matteo Rubinato de la Universidad de Coventry en el Reino Unido. Su charla se titula Investigación experimental y numérica del intercambio de flujos en inundaciones urbanas. En un momento más lo estaremos presentando. Esta charla será en inglés. Y yo quiero comentarles que esta sesión está siendo grabada para que de forma íntegra, una vez terminada y la procesemos rápidamente, pues pueda quedar como material de consulta posterior para todas y todos ustedes que nos acompañan a través de las plataformas digitales del Instituto Mexicano de Tecnología del Agua y de la Cátedra UNESCO. Y también, si saben de alguien que esté interesado en esta temática y por alguna razón no pudo acompañarnos en esta ocasión, pues ahí va a estar el material disponible para todas y para todos ustedes. También comentarles que como ustedes habrán notado, los micrófonos y las cámaras están por el momento cerrados para los participantes y así van a permanecer a lo largo de la sesión para pues asegurar la mejor fluidez y la mejor experiencia de escucha y de intercambio con todos nosotros y con nuestro experto de esta mañana, y la forma de establecer el diálogo y establecer este espacio para sus preguntas y comentarios será a través del chat. Quienes están directamente en la plataforma de Zoom, pues en el menú inferior está la opción para entrar al chat y ahí poder poner sus preguntas y sus comentarios para el doctor Rubinato en cualquier momento a partir del inicio de su charla. Y también a quienes nos acompañan a través de redes sociales, estamos transmitiendo totalmente en vivo a través de Facebook Live y también a través de Twitter. Entonces, pues ahí también estaremos muy al pendiente de sus intervenciones, de sus comentarios, y nos dará mucho gusto saber de ustedes y que nos están acompañando en esta comunidad del conocimiento que nos une a diferentes regiones del país, de México, a diferentes regiones de nuestro continente. Muchas gracias por acompañarnos y también nos ligan con nuestro experto de esta mañana, con el doctor Matteo Rubinato de la Universidad de Coventry hasta el Reino Unido. Y pues para hacer la presentación del tema y de nuestro invitado de esta mañana, bueno, esta tarde para el doctor Rubinato en Europa, quien llevará la moderación de este bloque y la presentación del doctor Rubinato y del tema será el doctor Laurent Curti, el coordinador de hidráulica en el Instituto Mexicano de Tecnología del Agua, a quien tengo muchísimo gusto de saludar esta mañana y dejarlo en el uso de la palabra. Y a partir de este momento, bueno, pues la charla se llevará a cabo en inglés. Tus preguntas las puedes hacer en español o en inglés, es indistinto, como tú lo prefieras. El tema es cómo abrir este espacio de diálogo al final de la presentación del doctor Rubinato. Entonces, sin más preámbulo, saludo con muchísimo gusto al doctor Laurent Curti. Laurent, ¿cómo estás? Muy, muy buenos días. Qué gusto saludarte esta mañana.
Hola Marco, muchas gracias. Buenos días a todos. Y como dijo Marco, pues ya voy a cambiar en inglés. Thank you very much everyone for joining us. So as Marco said, I'm Laurent Curti. I'm the head of hydraulics at the Mexican Institute of Water Technology. And I have the pleasure to present you Dr. Rubinato, who's one of the leaders in large-scale physical modeling in urban floods in the UK. And the main focus of his research involves novel quantification and explanation of flow processes in sewers and linked urban surfaces. Furthermore, Dr. Rubinato's research also explores engineering in the field of environmental fluid mechanics, typical of river and coastal environment, to develop innovative and useful approaches to help reduce the vulnerability, as well as enhance the resilience, adaptive capacity, and sustainability of environmental systems around the world in the face of increasing challenges, uncertainty, and climate change variability. So really, it's a great honor to have Dr. Rubinato with us today, because his talk will be about the interchange between the surface flow and drainage system in urban environment. As you may know, it's very, in case of urban flooding, we have special system designed to drain it, and to prevent urban flooding in the form of urban drainage, and how the water flow inside the drainage or outside the drainage to the surface is a very important topic to be able to understand better urban floods. It's a topic that I worked on myself, and I had the pleasure to meet Matteo in some conferences on the subject. So Matteo, as I said, is one of the leaders in the UK and maybe in the world on investigating this type of subject about the interaction between surface flow and drainage. So thank you, Matteo, for being here. And now the screen is yours. And yeah, please enlighten us on the subject.
Okay, so firstly, good afternoon, everyone. If you are in the UK, or good morning, of course, if you are in Mexico or in another country in Central America or South America. And I want to say thank you as well to Laura for this remarkable opportunity. And I hope that with this talk, you will get to know more about what I do. And who knows, probably it will be great if we can even start some collaboration or joint works with people that are listening to it. So before I start with the presentation, I want to just introduce myself and why I got this passion to become an environmental experimental modeler. So when I was doing my master studies in Italy at the University of Padova, actually the topic of my master thesis was building a physical scale model 1 to 43 of this dam that is called Dam of Morelli in Italy, because there was the need to expand the capability for releasing a higher quantity of water, because there was a sedimentation happening in the reservoir upstream, which was limiting the capacity of the storage. So during these years, when I was finishing my master's in Italy, is where I get to know and work with leaders in Italy at the University of Padova, and where I got this passion for experimental modeling. And since then, I was able to continue and grow. And today I will talk about the topic that regards the urban flooding, which is the image on the top left that I will describe in a few minutes. However, I've been working as well on experimental models for river situations, studied the effect the pollutant may have once it's dealing with vegetation on the sides of the river, as well as the breeze flow that you can see at the bottom right. And these are within universities in the UK, mainly Sheffield and Coventry University, as well as universities in China. The bottom left model is from Sichuan University in Chengdu, and the bottom right corner is the one that I've done in collaboration with the University in Beijing. So why do I think that this is an important topic? And hopefully you will all agree with me. I think that this is a worldwide problem. It is something that is affecting not just a single city in Italy or in the UK, but many cities across the world are affected by this issue. And what is actually more important is that we are expecting this phenomenon to become more frequent in the future. And when I talk about more frequent, it is because it can increase its magnitude, and also it can increase its frequency. And this is due to three important aspects. The first one is the climate change. We all know that there are changes within climates around across the world. And the most important thing is that there are situations in which, in certain areas, there are more heavy rainfall events that are becoming more frequent, and therefore they stress the existing sewer system. The second one, of course, is the increase of urbanization. And this is, again, another phenomenon that is seeing a lot of people moving from rural areas into urban areas. So when we think about that, and we think about the existing sewer systems, we can immediately realize that they've been designed with a lower capacity of water to be conveyed. And with more people moving into cities, into urban areas, they are able to not cope with the situation, and therefore they can lead to flooding. And the final one is related to the conditions of existing sewer systems. And this is just a picture, for example, from something that happened in the UK. But of course, I focus my research mainly here because it's where I work at the university, and most of the sewer systems here are from the Victorian era. So we're talking about hundreds of years ago. And this means that if not treated, they may lead the deposition of material, and they may lead to blockages, which consequently causes local flooding. So all these three aspects that are common across the world are actually increasing the possibility that we may have a flooding event in any of the cities across the world. I wanted as well to summarize, to try to identify all different topics that actually could be associated with the importance of flood modeling. So hopefully within the audience today, you can see your topic and your work within one of the bullet points here. When we try to predict urban flooding, nowadays engineers, they use tools, numerical tools, to try to identify, to produce maps that can actually estimate the level of flooding, which are the areas more at risk. And this can be for just designing new system, or producing hazard maps, or systems for real-time management, as well as also maps to actually contact rescue services and tell where to direct all the resources for a better management of the situation. And if we look at each one of these bullet points here, what actually is very important is that they all have to deal with the interaction between what happens in the sewers and what happens on the streets. And what actually is very, very important, and we need to state that, is that this type of flooding, because of course we also know that we have the possibility of river flooding and coastal flooding, what is associated with the urban flooding is considered to be the hardest type of flooding to predict and defend against. So we're dealing with a level of uncertainty that nowadays is still extremely active. So when we consider these numerical models here, nowadays there is a huge variety of possibilities we're working on. So we have 1D numerical models, we have 2D numerical models, and then of course we can link the two by using the specific nodes that could be Gurley's nodes for connecting the two different systems. And when we talk about numerical models, we definitely need to think about what could be the parameters that we input into the system to actually obtain what are the outputs of the flooding map. And as an input for a numerical model, typically we may have rainfall runoff, the typology of the pipe network, the digital elevation model, the different material of the pipes, and consequently the roughness of the pipes, and also how are the energy losses within the system. Each one of them incorporates a level of uncertainty that can lead to accurate or not accurate results at the end of the simulation. So thinking about those, actually, how can we make sure that whatever we test is extremely accurate? So to do that one, nowadays there are, the only capability that we have is using some resources, like for example, the picture here at the bottom left, where in some cities, this is actually in Sheffield, where I used to live for 11 years. Like here, they have recorded the level of the flooding at specific times of the year. So this could be an example of the water level that we can calibrate our model again. However, due to the development of social media, we can see how many people are actually taking videos, pictures, or whatever you can think about during these situations. And these are the only images, the only videos that we can actually use to calibrate and validate our models. However, they're not extremely accurate. So there is still a level of uncertainty with it. And this will not lead to 100% accuracy of what we are trying to achieve. And when we try to think about all of this, we can imagine straight away that due to the uncertainty of urban flooding event, we do not know when is going to be the next event. And even if we may know when it's going to be, we may not have the resources to actually develop a system of equipment that can measure everything that we need. Flow exchange, flow rates in the pipes and on the streets, velocity profiles. So all of this is leading to a lack of data, a paucity of data that actually makes more difficult to rely and to trust these numerical models. So what I want to do with my research, and this is what I started a few years ago, was to develop an experimental laboratory which could provide a better understanding of this phenomenon and try to further investigate every single assumption that has been made with numerical models, and at the same time provide high resolution data that could be controlled, but at the same time could be replicating the same scenarios of urban flooding and be used as a benchmark for numerical models. And this is also in line with at least the strategies here in the UK. I will be very glad to hear about what is the strategy, for example, in Mexico. But here, there are three crucial points that are directly in line with this type of research, because the government is trying to provide a better understanding of urban flooding scenarios. And there is a need to provide data that could be used to calibrate and validate numerical models, because they want to improve their accuracy. And all of this is targeting innovation for improving the development of new infrastructure. And it's also, at the same time, linked with what we call the GCRF Sustainable Development Goals, because for each one of the category that we have right here, and thinking about what I try to propose with my work, is actually in line with 3 different Sustainable Development Goals. So the first one is to try to target developments to build resilient infrastructure. So systems that actually lead to a non-flooding scenario, or even to resilient systems that can deal with the flooding scenario. And we want to make cities more sustainable and also safe. And finally, we are definitely targeting the issues of climate change. So these are 3 important criteria that are in line with the research that I'm proposing today, that I'm providing all the results to you. How did I do that? So I basically designed this experimental facility, which was built from scratch. And as you can see here in the schema, we have a sewer pipe, which is linked to an urban surface, which has a slope of 1 to 1000, via, in this case, a single manhole. This facility can also be expanded up to 6 manholes and 3 different pipes on the drainage. But to go back to try to provide a better understanding, we had to start from the basic scenario, because you try to understand firstly how a numerical model works on replicating the basic scenario, and then you increase its complexity. As you can see from the model here, you can measure upstream and downstream the flow for the inlet both on the sewer and on the surface, as well as the outflow on the sewer and on the surface. This is very important because it leads us to quantify a parameter that would be impossible to quantify in a real scenario, the flow exchange. Because by simply doing a mass balance between in and out in both systems, we can quantify how much is the flow that either exits the sewer or enters the drainage system. And this is actually an extremely important parameter, because if you think about any city around the world and you're trying to model it, there is no way actually, unless you have a flow meter in that specific manhole, that can tell you how much is the flow that is exiting during a flooding scenario. We have along the system pressure transducers that I will show now in a second. And there are also a set of measurements on the top of the surface, which actually are very important to determine what is the water level that we have on top of the surface around the manhole when we have the flooding scenario. Here, there are some more images that can give you probably a better understanding about the model. So the model was made in acrylic, and the choice was made because it is a material that is easy to deal with, to cut, and at the same time, it could enable the visualization of whatever was going inside the manhole. And you can see the example of the flow, electromagnetic flow meter in blue, and the valve opening in red. And in this case, this flow electromagnetic flow meter had an accuracy of plus and minus 2.5%. And for the flow measurement, basically we conducted an interpolation between the valve opening and the flow that was generated. And for the pressure transducers, we used the GEMS sensors, which had an accuracy of plus minus 0.72 millimeters. So we're talking about extremely accurate measurements. And below here, you see a view from the top of the facility, of the surface, which is 4 meters times 8. And at the moment, of course, this is just the image with one manhole overflowing. But as I said, this could be expanded to other 6 manholes from previous studies if you look at my previous publication. When I was designing this, I needed to make sure that everything that I designed in terms of equipment could be measured and could be controlled in real time. So I basically designed by using equipment provided by Labio, a system of connections that could provide, transform the electrical output of each equipment into a specific value, which could be liter per second for the flow rate or millimeters of water level for the water depth around the manhole. And this was the interface that I could see when I was doing my test. So I could see in real time the water level around the manhole. I could see the pressure upstream, downstream, and in the manhole itself. The different water levels for the emergency button when I was stopping it, when I was flooding the lab, which actually happened a few times when I was at the beginning stage of the test. And this is actually quite important because when I did the calibration between the valve opening and the flow in liter per second, I was not just using a steady condition for my test, because if you think about it, a normal flooding event is actually an extremely unsteady situation. So I was also able, with one of my first publications, to actually take specific rainfall events, generate flow hydrographs, and then scale with a direct interpolation, so using the same equation but reversing it from liter per second into the valve opening, and then simulating also specific hydrograph within the facility itself. So in terms of what can this facility do, we have 4 specific scenarios that are typical of an urban flooding. So you have the first one, which is the inflow into an unsurcharged sewer. This is what is called a free weir more often. So you have the water that basically is running on the streets and enters the sewer, which is not overflowing. The second one is called the submerged case. So you have inflow again from the street, from the water, that enters the manhole, which in this case is almost starting to come out from the drainage system. And then we have the last 2, which are basically situations in which you have an overflow from the drainage system, and you may have or not a combination of this interaction with water on the streets. And typically these scenarios are called the orifice scenario as well. So here you see a set of 3 equations that are used across the world by numerical modelers when trying to replicate within their models the link between sewer systems and urban surfaces. And what actually is very important when I did my literature review was that these equations have been never tested for a specific configuration like this one. They've been taken for different applications, but actually they were never validated against specific experimental models that could combine what is the interaction between the 2 systems. So what I did, like on one of my first studies, and was to try to check their validity. So this table here, I don't want to scare you. It's just an example that I just wanted to screenshot, because every time that I publish a document, I make available every single dataset that I have collected, so that whoever is interested on calibrating and validating their model can actually take my data. And as you can see here, there are some parameters that, of course, can be expanded with more data that are attached to the paper in terms of flow rates, what is the flow exchange. But I always put as well the non-dimensional numbers of fluid and also the Reynolds in the pipe, because I give the possibility to people to upscale these results to a different system. And especially when they have a different relationship between water level on the surface and the diameter of the manhole itself. So to verify that validity, I ran a series of tests. And as you can see here, basically, I plotted those equations against the flow exchange. And the fact that all of them got a linear interpolation basically confirmed the possibility of using this equation for this specific scenario. And as you may see on each graph, you have a band. So you have a middle interpolation, and then you have a plus and minus. This is because I wanted to incorporate within my result the error that I had due to the uncertainty associated with the flow measurements, because as I said, I could measure it either by using the mass balance on the sewer or using the mass balance on the surface. So to guarantee that my range of coefficient was within that band, I prefer to incorporate that uncertainty. And by looking at this equation, I didn't only validate those equations, but I also provided my coefficients in those three equations that I showed before, which can be used actually by numerical modelers when they insert those equations in their models. So they have a full set of data that now they can use and fit those equations and validate the outcomes of their models within my results, my experimental results. So this was the first step. These were all steady tests. So I wanted as well to see how the model could actually perform if I was running unsteady tests. So as you can see here, I ran a series of steady tests that were increasing their duration. And at the same time, we basically tested them against different conditions for the numerical modeling, which could be using different values, for example, of water level on the surface, or using the water level thanks to the equation of Manning, or even the water level using the manual height. And for each of them, as you can see from the graphs, so the black ones are experimental, so you can see that for each of them, basically every single configuration tends to overestimate the calculation of the flow exchange. So if you keep this in mind, this is just one system with one manual. So try to picture this image here. If you have to run a full city, how many other manuals there are, and how the level of uncertainty keeps increasing, from one to another. So we're talking about producing maps that are actually much more confusing and less accurate than what it could actually be. And this is something that recently I've also experienced with that I wanted to expand with a further research, and something else is under solution that I couldn't present you today. The second thing that I wanted to focus on was that all the tests that you saw before were made on the worst case scenario when actually the manual lead was removed due to the flooding event. However, this is not always the case, because there are situations in which the lead stay stuck to the manual. So when I was traveling around the world for conferences for my holidays, I was not only take good pictures of buildings and architecture, but I was focusing as well on different manual leads. And these are actually manual leads that I took from different countries across the world. And what I wanted to do was to actually see how, of course, by changing those equations based on the void area where the water could enter due to the different shape of these manuals, I wanted to see how actually this could perform, if there was a difference between one and the other. So I took again my scenario with all the measurements across, and I was able to identify one point where actually the water level was not either affected by the overflow of the water, or by the fact that when you have the weird scenarios, the water enters the manual, it was not in a location where the crest was already decreasing. So it was unaffected by it. And it could be the perfect measurement to actually validate these equations. And actually, you can clearly see already that they all produce a different water level. So upstream the conditions, we may have a different water depth, which actually can alter the amount of flow that is exchanged between the two systems. And after further investigating this, I could find the grade H, which is the one that you see on figure here, was the one that actually was enabling the less flow exchange. And probably this is obvious because you can see it's the one with the less amount of void area. However, the one with not the biggest amount of void area, which is grade A, still enable a higher flow exchange between all the other cases. So this made me thinking that it doesn't only matter on the empty space that you have within the lid, but it actually matters the geometry that you have and how the water is actually facilitated to enter the manual itself. So this made me thinking I need to investigate the velocity profile around these lids here, because this can justify why I got a higher flow exchange there than in other situations. And when actually I did this, I also focused on trying to apply those orifice equations with equations you saw before, and they were still validated even if I had different profiles. So they were still valid, and of course each of them got a specific set of coefficients. And what actually was another parameter that I needed to further investigate, which was, if you remember from what I said at the beginning, a part of uncertainty within numerical models, it is related to energy losses. So within my literature review, I was able to find that nowadays many people focused on this topic, and they did a lot of tests. I mean, they were able to focus on different flow situations, so subcritical, supercritical flow. They were able to focus on the different geometry of the manhole versus the pipe. They were able to see how the angle joins from the pipe to the manhole itself. And they were all absolutely extremely important studies. However, when we talk about the situation in sewers and manholes, we still talk about a variety of tests which only focused on the sewer system. But none of them is actually focused on the local losses when there is the flooding scenario. So these were still yet to be investigated when I did this study. And actually, this is important because without calibrating this parameter, we will never be sure or safe about the results that we produce with the numerical models. So what I did was running a series of tests to actually test these conditions and estimate the energy losses for this facility. So as you can see here, I also introduced a lid which could fully close the manhole and just enable a small stream of water coming out on the sides, as you normally see. And I could measure the pressure upstream and downstream the manhole. And I ran two sets of tests. So the first one was just increasing the capacity of the flow that was exiting the sewer. And I tested this one with and without the lid on the top of the manhole. The second series of tests was also to replicate an issue in the UK, which is a blockage on the pipe. And by increasing that blockage, see how the water was coming out would interfere with water running on the street. To do so, I also introduced a new method to estimate energy losses during a flooding scenario. So based on the mass balance between what comes in and what comes out, I was able to focus on what are basically two streams. So you have a stream of water that exits the manhole and a stream of water that actually follows the pipes. This leads to two different energy loss coefficients, one associated with the exchange and one associated with what exits the pipe. And I was able to rearrange all these equations to find specific coefficient for each stream. So let's see then how these coefficients behave based on the set of tests that I ran. So focusing on the first set, so remember, you increase the water of what comes out of the manhole and we have or not a lid on top. So what you could see here is that you have three set of graphs here, so 1, 2, and 3. The first one is just about the stream that goes out of the pipe. The second one is about the stream that exits the pipe, and then we have the overall coefficient. We combine the effects. So as you can see here, basically this is divides the situation from non-surcharge to surcharge. So when we don't have surcharge, it doesn't matter if we have a lid or not on the top of the manhole, and this has been proved absolutely fine. However, when we start having surcharge, we may see that the configuration without the lid has a different set of energy losses than the configuration with the lids, which again, it is good that happen because you will expect that if the water is trapped by the manhole, you will create more turbulence for the water to actually try to push and go out. If we look at just the stream when we have the part of the water exiting the system, there is a clear evidence that the lid may have an effect on the energy losses. And then, of course, if we combine, we're expecting to have some sort of similar scenario to the one of what goes out of the pipe. So this is very interesting because it shows how whenever we run and we test numerical models for cities, actually is very important if we know the typology of the lead on top of them, not just specific one that we may not be aware of. And for the second case, we actually, remember, blocked the pipe downstream, so simulated different set of pressure. And what you can see here again, 3 graphs. So again, first one is the one that follows the pipe. Then you have the one that exits the pipe, and then you have the overall situation. As you can see on the first one, there is a trend based on the increasing of the blockage, which at some point is actually broken. That means that we reach a level of turbulence inside the manhole that by reaching that one, there is no more linear increase. So something is so confused inside the manhole, so turbulent, so mixed, that actually breaks that type of relationship. What is actually very, very important is that it doesn't matter how much blockage we have downstream of the pipe, but the energy loss associated with what exits the manhole actually doesn't have any specific modification based on the amount of water we have on the surface. Because as you can see, we have a range of linear interpolations that are very, very, very similar and with a close range. So this is actually very important because it shows how it doesn't really matter how much water you have on the surface and how much is the blockage in your pipe. So this is actually something that, if taken into consideration in advance, can reduce the uncertainty. Then I also wanted to simulate these type of scenarios with a numerical model. So we used in this case SWIM, and as you can see here, you have 3 graphs on the left-hand side, which are without the lead configuration. The 3 on the right-hand side are with the lead. The 3 graphs that you have on both sides are related to the pressure upstream in the manhole and downstream the manhole. And then you have also another division within the graph, because this black dashed line here divides the non-surcharge case to the overflow case. So if you look at all the 6, on the left-hand side of the black dashed line, you see that experimental versus numerical results. So the green squares and the yellow and the orange circles are actually very similar. So there is no difficulty for the numerical models to actually replicate non-surcharge conditions. We start seeing, however, a different situation when we focus on the overflow, on the flow scenario. So you can see here, especially when we have a lead, which is again typical scenario that we will expect, that this leads to an uncertainty that once again was demonstrated to be present on numerical models. So with all my studies, I continue to actually show what needed to be taken into account and what could lead to more accurate results in the future. And this is another study where actually I focused on how the numerical models were good at replicating the flow exiting the manhole. So these are all screenshots where you can see we increased the ratio between what was coming out of the sewer and the flow on the surface. And the red dots are actually where the measurements were. And you can see how actually we start from a crescent moon shape of the area of transition from supercritical to subcritical flow within the manhole, and now actually we almost arrive to a fully developed circle that of course can be similar to almost a quadratic shape based on the assumption that we had with the numerical models. And this is just a visualization, but also in terms of results, you can see how there are still some limitations based on some assumptions on how the pressure, especially upstream and downstream the manhole, could be present in the numerical models. And this is important because these are the parameters that we would use to estimate the exchange between the two systems. And once I did all these tests, everything that I talked about so far was based on focusing on the flow conditions and on the hydraulics of it. However, if you go back a few minutes, you remember that I said to you that I wanted to focus on what was happening in terms of velocity conditions. So I designed this system. This is basically a particle dispenser. So there is a hopper here, and it contains PVC particles. And this pneumatic vibrator basically shakes the box. So the particles are moving towards the bottom side, and this roller brush here releases them into the system. So as you can see here, basically they are released steadily within the system. And then, of course, I had to design a system to collect the particles before they were going to recycle. And I did this because then I could develop a system of cameras which could record in real time all the videos that I was making and actually enable me to analyze step by step each of the movement of the particles from frame to frame to design what was the velocity field. I used GoPro cameras because not always you have huge availability of resources for research. And they have demonstrated to be actually very good. So I need to calibrate them because they have a fisheye effect. So I use this checkerboard here at the bottom. And once I have a full view of the system, I have to repeat this from water level to water level. And this is the image that a normal GoPro camera will give you. So you can see this fisheye effect with the curvature on the side. However, by implementing some algorithm with MATLAB function, I could dewarp the image and then crop it to make exactly the same platform as if it was straight in front of me without any curvature. And once I did that and I designed the system to be able to collect this data, I tested again all the lead, and I was able to not only verify experimentally and numerically the quantification of flow exchange, but at the same time, for each one of the lead, I was able to produce the full set of maps for the velocity field around it. And this one helped us to justify why the water was entering more easily for specific manual leads than others. And again, this data is shared in another journal paper that is mentioned above here. After all of this, I wanted to keep increasing with the results of this facility. And I wanted to move into a topic that was actually not something that so far many people have actually tried to deal with, which is the modeling of the transport of contaminants in urban flood flows. So when we talk about this, of course, I found literature review that was mentioning this issue and plenty of newspapers that actually were referring to it. But what actually gave me the inspiration was when I went to a conference, the ICUD in Prague in 2017, and one of the keynote speakers actually talked about this issue, because this was something that there was the need for it. There is a need for calibrating and validating models also for the pollutant transport. And when we talk about it, you can see here a list of things that may actually alter the quantification of the pollutant transport and how they could lead to specific issues if they're not considered. So there is a variety of fields that can be expanded and needs to be expanded. And to do so, I had to improve again my facility. So I had to find a way that I could release a tracer that was definitely not, an hazard for the university regulation and could be easily be tracked. So I basically focused on using the rhodamine, this dye, and I tried to characterize how the rhodamine basically can become more fluorescent if exposed to green light. And when I realized this with a similar short test, as you can see on the bottom left here in the lab, what I did, and this was one of the first outcomes, you can see on the left-hand side the experiment with this dye mixing with the water and how by applying the calibration a numerical model will work, I basically applied it to my system. So I covered the entire surface with green lights to avoid also with reflective sheet any reflection from outside external light. And those reflections you see here due to the lights have been taken care of by being removed with the calibration. And I replicated all water levels in this facility. And for each of them, I have added a level of pollutant that give me like all the concentration I would expect within the test. And I had to mix 4 times 8 meters for probably more than 50 times. So you can imagine how long was the calibration. And once I did the calibration, I also adapted the facility to inject into the pipes the rhodamine. So I have a tank downstream which fully mixes the dye with water, then feeds the tank at the top, and by gravity basically feeds into the pipe. And then I can, at the same time, release not only the water that I can change in and out, but I can also change the pollutant that enters the system. So I can have a steady injection as I can have an unsteady pulse. And this is actually very important because at this state, the facility can do basically anything. And I also wanted to increase even more the complexity of the facility. by actually replicating different street profiles on top of it. So with a 3D printer, I was designing these plastic boxes, and the pipes that you see here are all connected because with a vacuum pipe, I was taking the air off so that they could be stuck in the facility and not move with the water. And I could at the same time, once release the pressure, move them and shape them as I wanted. And this was important because actually I could not only provide the flow exchange, but I could also provide maps in terms of pollutant transport. So these are some tests that I did. So you can see a normal rectangular street. You can see a street with parking slots on the sides, both sides, cars in the middle, meander situation, and then one with the manual on the side of the street. And this is as well the same exactly configuration with the manual from the top. And what I did here, this is just a preliminary set of tests. So they are just in a phase where they will test it even more. But you can see on the left-hand side, the experimental model that is recorded by the GoPro camera. And you can see on the numerical model, which still needs some tweak, especially on the zone where there is intersection between cameras. But it shows how actually you have the spread of the pollutant along the surface. So this is a full set of data that not only provides like the hydraulic conditions, but also provide for each single point in the facility the concentration of the pollutant, so a full set of transport pollutant maps that can be used by numerical models. And this was done for not only those, but also the full 6 configuration. And what is actually very important is that, as I said, this is just something that I'm working on at the moment. So you can clearly see that there are still some inconsistencies that I need to improve. However, there are actually already some scenarios that help us to identify which typology of parking slot or the location of the manual, where actually, as you can see on top here, could go the dye from one side on another one. And this is also based dependent on the flooding conditions. And the idea is to basically continue. I have collected more than 250 tests now, so they're all under analysis, and continue to produce all these different scenarios, because numerical models should be able to test and be validated against the easiest scenario, so normal flow on the pipe with no flow exchange, the situation where you have flow exchange from the surface into the sewer, and the one with the overflow. And if a numerical model can do that in terms of hydraulic point of view, but also in terms of velocity profiles and pollutant transport, then we will be able to calibrate also the ADE equations and being able to improve the accuracy of numerical models. And this, of course, will have a long-term impact in terms of how we can produce better maps for a better health for the humans that are living in all these areas, because we need to be able to identify where the polluted water goes, because you make a huge difference if it goes in the middle of nowhere, or if actually it goes where there is a playground where kids could be affected by it. And just to finish very quickly, this was a full set of tests done with a scale facility. But I'm collaborating now with 2 institutions, Sheffield University, which is this one, and they have the capability of using one of the 7 national infrastructures in the UK, and this is called ICARA. And this is basically exactly what I showed you in a scale model at a full scale. And they also won recently a European grant, so I will be glad to receive any one of you that is interested on this topic if you want to write some proposals and we can do it together. But at the same time, I'm also one of the research fellows that is designing this facility at IKT, which is the Institute for Underground Infrastructure in Germany, in Gelsenkirchen. And this is actually another facility, full scale, that will be used to actually replicate the full series of tests that I've done in a scale situation with also a full scale scenario and the additional combination of the rainfall on top. So I thank you for your attention, and I will be here to answer any question that you have. Thank you.
Thank you very much, Matteo. Very, very interesting. We have one question from the audience so far, which is it possible to integrate water-based solution on your model, and did you thought of it, and what do you think? Do you think it would be interesting to evaluate the impact of leads or green infrastructure on the model?
Yes, actually, yeah. This is something that so I wanted to do it already on my scale facility in Sheffield, and that was the idea of that was to change the roughness on the surface and adding some green spaces within it. But actually, this is something that will definitely be done. I mean, is one of the ideas that we are trying to achieve with the facility in Germany. So this one here, because this is exactly like what we're trying to do. On the top of this facility, and we're talking about a surface that, as it's written up here, 10 meters by 20. This will be a full, basically, street profile, which can incorporate green areas like the one that you can see on the image here. So there is definitely potential for that. And I think that is important because I personally would like as well to study how the polluted water acts when it reaches these green areas here. So my idea is to run the set of tests with these green spaces and then also collect by taking some samples from the soil, some column of soil, and see how not only the pollutants are developing within these green areas, but even testing a series of events one after the other, or like in parallel and with different flow conditions, and actually see what could be like the developing the growth of the specific pathogens.
Thank you. I have a set of questions myself about the use of weir and orifice equation. So you showed with your research that they could be applied successfully, but it made me think. Yeah, we proved that it could be applied, but is it the best really? And also, I wanted to ask you about there's been a study from Akiel and Slidowski like some years ago in Poland that they used the flume with variable slope, and they found out that the actual coefficient varied with the fruit number on the surface. I don't know if with your research, if this is consistent with your research. What is your thought about it?
Yeah, so when you mentioned the one in Poland, you actually are right. There are a few other places around the world that are using experimental facilities similar to the one that I developed in Sheffield. There are also variable slopes in Barcelona at Barcelona Technical University, and there is one in Japan. So my model could not alter the slope. So I was basically, I would say, limited on the type of hydraulic condition that I could replicate within the roads, within the street. And when I did some small tests in the laboratory, the one I could actually verify that the supercritical condition on the surface could alter, of course, the exchange in the system. Because if you imagine a big slope and the water runs down very fast, sometimes it finds difficulties on entering the manual itself. So there is definitely an interaction between the slope and the hydraulic condition, consequently, within what enters the manual and then the use of the coefficients. And this is the reason why this facility here was designed by considering like the possibility of testing a different slope within the urban streets, because I want to replicate also supercritical flow conditions that could actually help to quantify the coefficients under these conditions. So this is something that I learned from my scale facility, and I wanted to apply with the possibility of this new facility here. And in terms of in the equations that you mentioned at the beginning, so the weir and the orifice, I don't think that they are the best option. And I also tell why, because just recently, like a few weeks ago, I have submitted another paper that I couldn't present today because the results are under publication. So until they're published, I won't be able to share them. But I designed a new different method to estimate the flow exchange different from the application of the weir and orifice equation. And that demonstrated to be more efficient than the one with just those equations.
That's very interesting. Thank you. Yeah, please inform us when the article is published.
Yeah, definitely.
And I think one of the issue in Mexico, especially, is and in many other countries, is the impact of solids in the drainage network, especially garbage, basically, that can affect how the drainage network function and and especially how it is able to drain the surface. So how is it? What is your thought on it, and how could it be modeled and studied?
Yeah, so that actually, because I had to do a selection here when I was preparing this presentation, but I actually did as well works for a company in the UK, which is called Drainage Forest, when I was using this facility. And they gave me samples of debris from real street profiles. So you can imagine anything from leaves, so organic material, but as well as cigarettes or anything that you can imagine like running on the street. And they wanted me to test on the facility by using a set of gully bags made of polystyrol to see how this material could be trapped by the bugs inside the manholes, but at the same time verify if these bugs inside the manholes will alter the flow exchange. And I was able to demonstrate that actually the bugs that they designed were not altering the amount of water entering the sewer system. And for them, it was a success because basically to manage them, you just had to release these bugs, replace them with clean ones, and just wash the other out once you had all the dirty ones connected together. So I believe that was one of the solutions, but I also believe that there is so much to study within this specific topic, because as soon as I can, for example, I would like to study different blockages in the pipes upstream and downstream, even when I have manholes in series, because it would be nice to see how actually alters the water level from one manhole to another, and see if there is an equation that can be developed on providing some new equipment within municipalities and being able to trigger the point when actually we can understand in advance when the manhole downstream can actually flood. And we talk about, debris, sediments. This is something that, is definitely a topic that needs to be investigated, because whenever there is a flooding event, water is polluted. So that's why it was my main concern. But you also have sediment moving from the sewers to the streets. And this one sometimes may lead to deposition of material to manholes downstream and induce their blockage. So in terms of sediment transport, blockage, pollutant transport, these are all topics that can definitely be fully studied, and they still have a lack of presentation of results that needs to be provided.
Okay, thank you. I have a question from Alberto Rojas, related to the precedent question from Luis Puyo, that he suggests that on top of checking for green infrastructures, etc., suggests to integrate biodiversity into the model and see how it could impact the model. And another, yeah, sorry,
yeah,
go on.
No, go for it. Continue this for you. It was finished.
No, that's okay. So it's one comment, and if you want to comment on that comment, go ahead. I will continue with the other question.
Okay, yeah, I think that that's absolutely valid. I think that we will definitely take into consideration a variety of green areas and plants to see actually which one performs best on holding the water, storing the water, and reducing the amount of runoff. So in those green areas, as you see in this picture, we will probably start with normal grass, and then from there we will try to develop different systems. I'm also doing with a colleague at Coventry now a study on how different trees, based on their shape and all, as you can see here. Actually, you can see from this image, you can see that the links that you have of the tree itself within the ground that interacts with the pipe may also lead to specific blockages. So this is actually something important to consider, because we can study the biodiversity on top, but we also need to consider how this interacts with the underneath system. So the idea is to also use a transparent platform which enables the capability of seeing how the vegetation develops, grows, and how it interacts with different pipes material that we will test in the facility.
Okay, thank you. There's a question from Iskra Mejia Estrada, who asks, are there any plans to perform experiments on different pipe materials to see how their rugosity affects the flow exchange according to the grade types?
Yeah, definitely. Yeah, there is within this institute here, the IKT, they are leaders in Germany for actually validating the performance of pipes with different material for German water companies. So the idea is to actually incorporate all of them and actually see which one better performs, not only in terms of conveying the water, but in terms of durability, resistance to weather conditions, resistance to interaction with the vegetation. And this is why on this picture here you see the different colors, because they get to test different pipes with different roughness. And, this will be done as well for the street on top, because from my facility you could see that it was a smooth surface, and this was due to the scaling boundaries. But the idea is also to change that roughness on the surface by using different configuration, like for example asphalt or anything that can actually alter the roughness on top and change the flow of the water running on the streets.
Yeah, thank you. And actually, this leads to a follow-up question from myself. Okay. When we discussed earlier what type of experiment could be done on this type of facility, one interest is how to see. It's not related to the interchange of flow, but more on the street and the safety and the security of people on the street, and is how different slopes and flows and velocities and the surface of the street could affect how the civilian or the people on the street could be moved away from the water flow. And it's an issue in Mexico because it's a mountainous country. There are high flow velocities and sometimes very high level in the streets. And every year, unfortunately, there are people that are carried away by the flow in the streets. So it's an interest here to see, to try to find what threshold of water velocity or a water level become a security risk for the people, like for personal security. So yeah, that could be an interesting topic.
I think you are. That was a very good idea. It's something that I've seen in some models in Japan that gave me inspiration for that as well. The idea will be to have I mean, for this one, of course, we need to go through the risk assessment and everything, but the idea is to have a variety of people of different ages. So for example, from I don't know, 10 to 20, 30 to 40, and go on until older people. And by testing different water conditions and water profiles, of course, by enabling them to connect to something, to cords or to something that they can hold on in case they're falling down, being able to produce an estimation of what could be a specific water profile based on a specific slope or configuration, the limit that will trigger the instability of a human being walking on the street. So that is something else that is definitely links to your very good suggestion.
Okay, yeah, that could be a potential collaboration because at IMTA we had some years ago a model that were doing the same way. We were leaving people trying to cross the street with a flow, and we had a small street model, and there have been different tests with different slopes and different water levels and different. I think if I remember well, different type of soles of the shoes that people were wearing that could affect how their stability in the flow. So okay. Yeah, that could be interesting. And another question from the audience, from Luis Fuello as well, who asked if you're familiar with the drainage system of Mexico City and the complexity of it, and especially like the deep drainage system that there is in Mexico City.
I never worked actually with any institution in Mexico, so this was also something that I would really like to get as an outcome from today. Like, hopefully, anyone from the audience, that found this talk interesting, I really would be pleased if they can contact me, and we can actually discuss what is the situation in Mexico and if there is anything that I could do to help them in terms of testing the conditions that you actually are looking for in those specific cities. And this is exactly what I would really like to hear from anywhere in the audience, if there is anyone that is interested in continuing this talk another time and actually being able to create something that I could do to help them as well.
Okay, yeah, Mexico City is very, very complex from the water perspective and for the drainage. You may know that it's at the bottom of an underage basin, so underage catchment. So it's very difficult to drainage. Yeah, stormwater management is very difficult in Mexico City. So yeah, I don't know if there is not any more question from the audience. Then we can close the question session. And thank you very much, Matteo, again. And as you said, we will keep in touch. And if anyone from the audience is interested in discussing more detail with you, then we can share the details.
Excellent, excellent.
Yeah, and oh yeah, and sorry, I just Petronilo Cortes just commented that in our laboratory at IMTA, we have one of the largest hydraulic laboratory in Mexico. We have he said that we have a variable slope flume of 19 meters and many other experimental installations. So yeah, collaboration is definitely an option.
It sounds very good, because actually we could run different configuration with different systems and combine them. So it would be very good to do.
Okay, thank you very much, Matteo. And now I will return the microphone to Marco for the closing words. Thank you very much, Matteo. Very good presentation.
Thanks again for the opportunity, and thank you everyone for attending this session.
On the contrary, thank you, Matteo, for your presentation. It was excellent. There are many comments about your presentation, and congratulations. And it is great to have this opportunity to find some possibilities to collaborate with you. It would be great. Thank you very much. Y muchas gracias también, Lorán, por tu trabajo de moderación. Lorán Cortí, coordinador de hidráulica del Instituto Mexicano de Tecnología del Agua. Y pues yo quisiera invitarlos para cerrar este seminario a que, pues como es una tradición en estos espacios de conocimiento, quien así lo desee pueda encender su cámara para que podamos tomar una imagen del grupo, una foto del grupo, para dejar pues constancia de este magnífico espacio de conocimiento que tuvimos esta mañana, posible gracias por supuesto a la participación de todas y todos ustedes y de la presentación magnífica del doctor Matteo Rubinato. Yo quiero también aprovechar el momento hablando de potenciales de colaboración, pues como lo comentó el doctor Rubinato, pues todo este trabajo interesante, importante de observación, de experimentación, de modelación de inundaciones urbanas que se prevé que podrían ser cada vez más frecuentes, pues abre espacios y posibilidades de colaboración muy interesantes que por supuesto que nos encantaría pues mantener esta vinculación con el doctor Rubinato y por supuesto con todas y con todos ustedes que nos acompañan en esta transmisión. Yo quiero aprovechar rápidamente también para agradecer su presencia a través de redes sociales, a través de esta plataforma y a los interesados y compañeros y colegas de esta comunidad de conocimiento del agua que nos acompañan en esta ocasión de diferentes regiones de México, pero también desde Canadá, desde Ecuador, desde Paraguay, Colombia, Venezuela, Guatemala, en Haití también nos están acompañando. Un saludo también y un abrazo fuerte por allá a Honduras y por supuesto también en el Reino unido. Muchísimas gracias por estar con nosotros, acompañarnos, y en lo que van encendiendo sus cámaras, yo quisiera aprovechar también este instante para rápidamente hacer algunos avisos y algunas invitaciones para todas y todos ustedes de los próximos eventos y de la información que tendremos para todas y todos ustedes. Si vemos la siguiente, por favor. Esta imagen queda de recuerdo, y la próxima semana, el 19, perdón, el 12, 16, perdón, el 16 de abril tendremos la presentación del doctor Gabriel Díaz Hernández en torno a la gestión costera y portuaria, todo esto que tiene que ver con el estudio del agua, con sistemas operacionales de ayuda precisamente para la gestión costera y portuaria. Él nos acompaña desde la Universidad de Cantabria. El registro está ya abierto, ya pueden registrarse en la página de la Cátedra UNESCO IMTA, la Buena Ciudad del Conocimiento, que tenemos en la pantalla, y que puntualmente pues, nos acompañen y que nos veamos en la próxima charla con el doctor Gabriel Díaz Hernández. La próxima, por favor, vemos la siguiente. Los invitamos, por supuesto, a leernos y a compartir pues, opiniones o compartir perspectivas que tenemos en torno a diferentes temáticas del agua. Esta semana, equidad y justicia hídrica es una reflexión necesaria que involucre y que incluya las dimensiones sociales en torno al agua. Esta columna está publicada en este tema en particular esta semana en la página del Instituto Mexicano de Tecnología del Agua, y cada semana tenemos un tema diferente. Todos los lunes muy temprano están estos temas que proponemos ustedes en la agenda de discusión, en la agenda de conversación en torno al agua. La siguiente, por favor. Los invitamos, por supuesto, a conocer más de las actividades de los grupos de trabajo del Instituto Mexicano de Tecnología del Agua y cómo nos vinculamos con diferentes instituciones y diferentes sectores de la sociedad para poder hacer que el conocimiento y la tecnología del agua pues sean un elemento para la equidad y para un desarrollo equitativo y el cuidado, por supuesto, del ambiente. Los invitamos también, nuestro reporte lo encuentran en la página institucional. La siguiente, por favor. Bueno, los invitamos también a conocer más de nuestra organización interna, notas muy interesantes en este número de El Acueducto, nuestra gaceta institucional, conocer más de la temática que tiene que ver con calidad del agua, con las actividades internacionales, institucionales, en fin, conocimiento, divulgación, leyendas, cuentos, un área de entretenimiento también súper interesante en torno al agua. Les invitamos a que nos visiten en nuestras redes sociales y, por supuesto, en nuestro sitio institucional para que conozcan más de todas estas líneas de actividad que compartimos con todas y todos ustedes. La siguiente, por favor. Y queremos hacerles también invitaciones para desarrollo profesional y también para desarrollo de capacidades, una de las líneas importantes de la labor sustantiva del instituto. En nuestras páginas de educación continua y del posgrado podrán encontrar invitaciones a cursos. Por ejemplo, tenemos ya abierta la convocatoria a un curso de operación de plantas de tratamiento de lodos activados, un curso importante, interesante para todas y todos interesados, o si sabes de alguien que pueda beneficiarse de este curso, por favor compartirle la información, y que todo esto está en nuestras redes sociales y también está en nuestros sitios institucionales. Como este curso, tenemos ya toda la programación de cursos publicada para que este u otros temas de tu interés puedas pues aprovechar estas oportunidades de desarrollo de capacidades. La siguiente, por favor. Y recordarles también que las convocatorias a las maestrías y posgrados del Instituto Mexicano de Tecnología del Agua están abiertos en la página del posgrado, la tenemos a la vista en la pantalla. En particular, los quiero animar a que pues quien esté interesado en aprovechar este programa de maestría en gestión de recursos hídricos, que es en línea, es a distancia, pues pueda aprovecharlo. La convocatoria se cierra el 16 de abril y ahí encontrarán todos los requisitos, los procedimientos, y nos encantaría que formes parte de la comunidad del posgrado del Instituto Mexicano de Tecnología del Agua, nos ayudes a canalizar o invitar a alguien que pudiera beneficiarse también de este esquema de formación profesional. La siguiente, por favor. Y bueno, recordarles simplemente pues que ahí nos encontramos en nuestras redes sociales y que es una forma inmejorable para poder mantenernos en contacto en estos tiempos en los que tal vez el contacto directo, el contacto físico no es tan factible, pero ese es el vehículo para que podamos mantenernos al tanto e informados. Nos gustaría muchísimo verlos por ahí y también conocer cuáles son sus propuestas, sus ideas y sus sugerencias para mejorar estos mecanismos de comunicación y de difusión con todas y con todos ustedes. Creo que esta es la última lámina, entonces si podemos dejar de compartir la pantalla y quienes así lo deseen poder encender nuestras cámaras para poder tomar esta imagen de grupo, agradeciéndoles muchísimo el favor de su atención, su participación interesante siempre en este diálogo. Por supuesto, al doctor Matteo Rubinato. Thank you very much again, Matteo, for being with us today. And we hope we can see you again very soon.
Definitely. Thank you again for the opportunity. I really appreciate it.
Thank you very much. Pues estamos listos entonces con el equipo de comunicación. Muchísimas gracias a todas las compañeras y compañeros que hacen posible también esta producción y esta transmisión. Y pues simplemente para decirles que a la cuenta de 3 podríamos regalarnos tal vez nuestra mejor sonrisa de viernes, además sonrisa de viernes tiene que ser hoy, para pues festejar el cierre de este espacio de conocimiento y para desearnos un gran fin de semana y una semana entrante pues igual de productiva o mejor productiva que la que tuvimos esta semana, y esperando vernos muy, muy pronto. Entonces, a la cuenta de 3 hacemos estas tomas para poder registrar esta participación de nuestro seminario de hoy. A la cuenta de 3, 1, 2 y 3, nos regalamos una gran sonrisa. Muchas gracias por acompañarnos. Y a lo mejor hacemos una segunda toma, y con esta segunda toma despedirnos y desearles que tengan un gran fin de semana y pedirles atentamente que nos sigamos cuidando y nos veamos muy, muy pronto en un espacio de conocimiento, en el próximo espacio de conocimiento. A la cuenta de 3 nos regalamos una sonrisa y nos despedimos. Muchísimas gracias. 1, 2 y 3. Muchísimas gracias. Nos vemos en el siguiente espacio de conocimiento. Thank you again, Mateo.
Thanks again, and have a nice weekend.
Yeah.
Thank you. Have a nice weekend. Thank you, everyone. Gracias a todos y que tengan un excelente viernes.
Muchas gracias, Loran.
If you have 1 minute, Loran, to stay online, just 1 minute when everything is
okay.
Thank you.
Yes, for sure.